Hi, my name is Tejasvi KY. Along with my teammates Toshita L and Nisarga Osmani, we have developed a project titled Smart Factory Monitoring System using IoT during the internship period of Emertxe IoT Internship, and what we have learned, that and all we explain here. Introduction. Internet of Things IoT is a network of physical devices connected to the internet that can collect and exchange data. This device includes sensors, appliances, vehicles, machines embedded with software and connectivity. IoT enable device to communicate with each other with or without human inventions. It helps in real-time monitoring and control automation of systems. IoT is widely used for smart homes, healthcare applications, agriculture and industries. Overall, it improves efficiency, accuracy, and convenience in the daily life. And applications of IoT are smart home, healthcare, agriculture, smart cities, industrial IoT, and transportation. Uses of IoT, mainly it is used for remote monitoring and controlling, and automation, data collection, improvement efficiency, better decision making, safety and security, cost reduction. Architecture of IoT. The layer 1 consists of DST2 sensor and LM35 humidity sensors and PIR LDR sensors and Arduino Uno and relays and LEDs in the physical world. In the layer 2, the network and connectivity, mainly MQTT sensor, which is used for the connection between the layer 1 and layer 2 and to the layer 3 also. It is mainly having Ethernet shield with his WFI 5500 for connectivity. And in layer 3, it is mainly a cloud, which is ThingsBoard and MQTT broker and rule engine. In the layer 4, web dashboard, where we can see live charts, gauzes and alarms. The application layer provides dashboards, alerts, and mobile access user. Overall, the data flows from sensors to user, and control commands can be sent to the devices. And majorly, we have used Arduino Uno in the PICSimLab. Open source microcontroller board used for ATMEG 328P, widely used for prototyping and embedded system projects. Easily programmed using the IDE Playground or IDE tool, provides digital and analog input-output pins for interfacing components, operates on 5-volt power supply, USBs or external adapters, beginner friendly with simple hardware and coding, used in applications like robotics, I- IoT, and automation.
And overview of the project. The smart factory monitoring system. In a smart factory lighting system uses connected sensors, devices and platform like Arduino IDE to monitor and control optimization of industrial operation in real time. Communication is enabled using protocols such as MQTT. And environmental monitoring means sensors continuously track the temperature, humidity and air quality across the factory zones. This ensures proper working condition and protect equipments and maintain product quality. And productive maintenance sensors detects early signs of machine fault. This helps in preventing breakdown of the machines in real time and also save maintenance cost. Safety and emergency response. IoT system triggers automatic alert and shutdowns during emergencies, whether gas leakage or overheating. This improves worker safety and prevent major accidents. Productivity visibility. By using the real-time dashboards, shows the overall equipment effectiveness, machine performance, and bottlenecks. Manager can make faster and better decisions quickly. Remote control. Engineers can control machines remotely using relays, conveyors, through web or mobile dashboards. This increases flexibility and reduces manual effort. Trend analysis means during the AI world, it can store historical data and analyzes it and identify pattern and energy usage and inefficiency. This helps in cost reduction, optimization, and meeting of the diseffectiveness of faults. Thank you.
I'm Nisarga Osmani and I will be presenting system architecture of our project explaining how the components are structured and connected. This slide shows that three-tier IoT system architecture used in our project. At the bottom, we have the sensor layer, which includes sensors like DHT22, LM35, PIR, and LDR. These sensors collect real-time data such as temperature, humidity, motion, and light intensity. Above that is the edge layer where data is processed locally. Here we have node 1 for production line and node 2 for warehouse monitoring. These nodes gather sensor data and send it to the cloud. Next, it is the application layer, which includes ThingsBoard, rule engine, alarm manager, and time series database. This layer processes the data and applies rules, stores information, and generates alerts when needed. Finally, the presentation layer is where users interact with the system. It includes the web dashboard, REST API, and mobile app, allowing users to monitor and control the system remotely. And next slide, that is the block diagram. So that this diagram represents an IoT based monitoring system where multiple sensor nodes collect environmental data and send it to a cloud platform using MQTT protocol. The data is then visualized on a dashboard. So node 1 consists of Arduino Uno connected with sensors like DHT22 for temperature and humidity, LM35 for temperature and potentiometer to detect vibration. It has an IP address and continuously collects the environmental data. Node 2 also uses Arduino Uno with sensors such as DHT22 PIR sensor for motion detection and LDR for light intensity. It has IP address, and this node monitors motion and lightning conditions. Ethernet model, both nodes send data through Ethernet shield using CAT5 cables. It uses TCP and IP protocol and communicates with the server via SPI interface. Communication protocol, that is the MQTT. The data is transmitted using MQTT protocol, which is lightweight and suitable for IoT applications. ThingsBoard server, the data is received by ThingsBoard, which acts as an MQTT broker and processing unit. It includes a rule engine and database for storage and alarm manager for alerts. Dashboard, finally the processed data is displayed on a web dashboard where users can see live charts, receive notifications, and control devices using the RPC. Next slide is the node 1. It consists of DHT22. This sensor is digital sensor that measures and outputs accurate temperature and humidity data. LM35 is a precision sensor that measures temperature and gives output has a voltage proportional to the temperature. Potentiometer, the potentiometer is variable register used to adjust voltage and control current in a circuit. Relay, the relay is an electrically operated switch that uses a small current to control a large current circuit. And green, yellow, red LED, the LED is a semiconductor device that emits light when electric current flows through it. Push button is a simple switch that completes a circuit only when it is pressed. And node 2, it consists of DHT22, which is also known as a digital sensor that measures the temperature and humidity accurately and gives the output. And LDR is a sensor whose resistance changes based on the intensity of light falling on it. PIRHC SR501 is a sensor that detects human motion by sensing infrared radiation from moving objects. And project requirements are functional requirements, non-functional requirements, and simulatory requirements. So the first functional requirements are real-time sensor that it collects the data for every 5 seconds. Automated threshold based alerting, remote relay control via ThingsBoard dashboard. And historical trend analysis and data reporting, multi-node coordination for emergency scenarios, and MQTT telemetry publishing with JSON payload format. And non-functional requirements are end-to-end latency less than 5 seconds and system uptime more than 99%, scalable to 100 plus nodes, and MQTT message size is less than or equal to 256 bytes. Dashboard load time is less than 3 seconds. Then simulatory requirements: PICSimLab for Arduino Uno simulation, virtual sensors like DHT22, LM35, PIR, LDR, simulated Ethernet connectivity, and no physical hardware required, supports full firmware testing and MQTT.
Myself Toshita. In this presentation, I am going to explain you about the project requirements and the implementation of our project, that is Smart Factory Monitoring System. First, going towards the introduction, let me introduce ThingsBoard. It is an open source IoT platform used to manage devices, collect data and visualize it in a real time. In our system, sensors are connected to the Arduino which collects the data and data is sent using a MQTT. ThingsBoard processes and displays it on a dashboard. The architecture flow of the ThingsBoard is as follows. The sensors are connected to the MQTT broker. The MQTT broker is followed by the ThingsBoard server, and then with a database, then with a dashboard where the entire data is displayed in a dashboard. This helps the industries monitor machines efficiently. Next, let us see how ThingsBoard work. ThingsBoard mainly works in three parts: device management, real-time data visualization, rule engine and alerts. In device management, register and control devices from one place. In real-time data visualization, it shows the live graphs of temperature and humidity. In rule engine and alerts, automatically triggers alerts when limits are exceeded. For example, if we consider temperature, if the temperature is high, alert is generated instantly. Going forward, the MQTT and JSON. Let's understand the communication. MQTT. The MQTT stands for Message Queuing Telemetry Transport, which works on publish and subscribe model. These are the two models. Devices send data to a broker, platform subscribes and receives it. And a JSON. JSON is a JavaScript object notation which is very lightweight data format, which is very efficient and simple, and though this is used in the ThingsBoard. Uses a key value pairs, easy to read and transmit. For example, if temperature is 28, humidity 60. And going forward, MQTT publishing JSON payload format. Let us see how this format works. MQTT telemetry with JSON payload means sending machine sensor data to server in a structured format. Sensors like temperature, vibration, etc. collect the real-time data from the machines as it is connected to Arduino. The devices publish this data to an MQTT broker using a topic, for example, factory, machine 1 or data. Then the data is sent as a JSON payload like temperature 30, vibration 0.2, 0.02, status that is on. IoT platforms like ThingsBoard subscribe to these topics and receive the data. The platform processes it and shows dashboards and triggers alerts if values exceeds the limits. Then these are all displayed on the dashboard. Then going format for the simulation requirements. For the simulation we are using PICSimLab, which is not a hardware, but we can connect the hardware protocols like hardware components in the software, in a firmware. In PICSimLab is a simulation tool used to design and test microcontroller based circuits virtually, but we can't do it practically like a hands-on session and all. It allows you to simulate boards like PIC, Arduino and ESP without real hardware. You can connect sensors like LEDs and other components in a virtual environment also. Helps in testing code and circuit behavior before real implementation. Widely used for learning embedded systems and IoT projects. In this, we can't use the real hardware connections, but we can it enhances like that we are doing a real connections in a software requirements. Going towards the communication design requirements are protocol, where the protocol requires MQTT v3 1.1 over TCP and IP protocol Ethernet. Broker ThingsBoard for 1883 and 8883 TLS. QoS level is 1 at least once delivery. Keep alive is a 60 seconds. Payload format is a JSON, 150 bytes per message. Publish rate is every 5 seconds per node. Total throughput is 60 bytes per second for every 2 nodes. Reconnect strategy is back of 5 seconds to 60 seconds. Authentication is 250 bit device tokens. Going towards the implementation, this is the core part where the communication happens between the devices and the server. The first step in the MQTT protocol implementation is device setup. Each machine is connected to a controller like Arduino. Arduino acts as a controller and it is connected to a sensor. Sensors are connected to the Arduino. The sensors such as temperature sensor, vibration sensor collect the real-time data. The controller reads and prepares this data. So this is a data collection stage. The next stage is the MQTT connection. Devices connect to a ThingsBoard broker using a MQTT over TCP and IP protocol. MQTT uses a publish and subscribe model. Devices acts as a publishers and ThingsBoard acts as a subscriber. This ensures a efficient and lightweight communication. The next step is the data publishing. Collected data is converted into a JSON format, that is a JavaScript object notation format. For example, temperature 30, vibration 0.02 and data is sent to a topic. It is published at a regular intervals of time for every 5 seconds once. This allows the continuous monitoring. Next is reliability, that is a QoS. We use a QoS level 1. Ensures a message is delivered at least once. Even if network issues occur, data won't be lost. This is very important for an industrial safety system. Next step is the session management. The keep alive time is 60 seconds, where if the connection is lost, the system automatically reconnects. Ensures the continuous communication without any manual intervention. Next step is the security. Each device has a unique access token used for the authentication, which prevents the unauthorized access where the theft protection will be given. The next step is the processing and alerts. Once the data reaches the ThingsBoard, it is processed and the dashboard is updated. The data displayed on the dashboard will be updated once it will be sent to ThingsBoard. This completes the full IoT data cycle. This is how the implementation takes place. Next, going towards the results, the automated alert rules which is given. Now let's see the output of our system. In ThingsBoard, we create rules that automatically monitor data and take action. The first alert given is a temperature alert. If the temperature is greater than the 35 degrees Celsius, system generates a critical alert where giving the notifications which is sent via email or telegram, where the red LED turns on indicates the overheating of condition, which is not good. Next alert sent is vibration alert. If the vibration alert is if the vibration is more than 700, that is the ADC value, warning alert is triggered. Yellow LED glows, event is logged. This which helps to detect the machine faults early. The next alert detected is the humidity alert. If the humidity is exceeded above 80%, warning notification is sent, which is used for the environmental setup monitoring. The next part is the rule engine working, where the system continuously checks incoming data, automatically triggers the action. No human intervention required. This is a fully automated system where it avoids the manual intervention. Going towards the next slide, that is the future scope and enhancements. Now I will explain how the system can be improved in the future. First improvement can be AI based predictive maintenance. Use machine learning to predict failures and detect the problems before they occur. Before they occur, we can predict the failures and reduce the downtime and maintenance cost also. The next improvement is edge computing. Use devices like ESP32 to process the data locally, reduces the delay or latency. Faster responses compared to cloud only systems. The next improvement is advanced analytics dashboard. Add trend analysis and performance graph, provide a better insights and keen visits. Helps in decision making. The next one of the major improvement can be done is the mobile app integration, where it makes the human work very easy. Monitoring and control system uses using smartphones. Easy remote access from anywhere. Next is scalability factor. Expand systems to multiple factories, centralized cloud monitoring. This is very suitable for the large scale integration industries. And At last, finally, I would like to conclude that we implemented a smart factory monitoring system using a MQTT and ThingsBoard. It enables a real-time data monitoring, automation and alerts. This system is very reliable, scalable and efficient. Future improvements can make it even smarter using AI and edge computing. Thank you.